I'll Teams channel, I'll be uploading them, as well as I'll stop. So they will be uploaded on the Teams channel as well as on YouTube, which you'll be getting. And we'll have three sections to this course. First would be random processes, second will be the linear algebra, and third would be optimization. And for each of these around 4 weeks of classes, we would have four assignments, which would be used to grade people. And also, ma'am has asked me to take attendance. So that would be essential to you attend all these sessions and not view them as online lectures, recorded lectures, so that we have the interaction. Otherwise, I can record the lectures and upload it. That's not going to be useful. So let's interact. And so the class for on Saturdays, you don't have classes, right? So it's okay if you have afternoon around 4, 4, 3, 4 sessions.
Yes, there is no problem.
Okay,
We
so
have
Saturdays will have the same timing, or if we, okay, go ahead.
we have lab, ASM lab.
Somebody, you have lab
Yes, sir. Yes, sir.
up to what time?
And maybe up to 5:30 from say, in the second half, maybe.
Hello?
Hello.
Yeah, go ahead.
We may have ASM lab from 3:30 to 5:30.
So you have lab from 3:30 to 5:30.
Saturday.
But you had this initially, these were in the morning, right? Not you may have, as in you do
Because
not know this.
the other, I'm actually in section A2, so the section has been split. One part of the section will have lab in the first half, the other in the second half. And
I
we
see.
haven't been given the partitions yet.
So you have sessions up to class up to 3:30.
One batch will have lab from 10 to 2, other will have from 3:30 to 5:30. And yeah,
Okay. So how many of you are from the evening batch? So are there like if there are a lot of people, we'll have to do a different later time. But otherwise, you can like on Saturdays, which two classes you'll be seeing, you can see them once you come back. There are these two are the options. So are there a lot of people on Saturday who have lab, or it's just one or two? You can because I was planning, because I have some deliverables at the end of August, so I will not be able to conduct sessions then. So I was trying to complete as much as possible by the middle of August. Probably complete everything, all the sessions. We would, and then you can do your assignments happily, taking your time. I thought that's a good idea. So I was thinking Friday, Saturday, Sunday, we have three sessions on a go, and then that would be good.
this Saturday is fine because this Saturday is a holiday. This Saturday we
Okay,
can
then I don't think we'll have a lot of Saturdays. We maximum 2 Saturdays, and if there are any other things, so tomorrow we'll be having our session from say 3 or 3:30. I'll update that schedule, and then we can do. Let us have this first three sessions, and then we will take it a step at a time. Maybe we can have a class on the weekdays at from 9 as we are doing today, or we can have it next Friday as we are doing it today. We'll see that, because I'm a bit busy for a few weeks up to end of August, so we'll have to. I'll keep you posted 1 day or 2 day before the classes if they are happening on weekdays. But on the weekends, you on Saturdays and Sundays, Sunday in the morning, 2.5 hours, on Saturday 2.5 hours in the evening, we'll conduct these sessions. So and probably one class. So there'll be 10 of these sessions. So today, let us begin with I will slowly introduce you to the ideas of probability. Some of this may be very known facts to you all. You may have done this in class 10, 11 and 12, and also the seniors may have seen this earlier, but as we go ahead, we will be seeing that we would be learning new techniques that will not only be helpful for machine learning and also people who are interested in applying for GATE and so on, or interviews abroad. So there also it will be useful. So let's start. So if you have any questions, I'll take them now, or we'll start off and then we can go. So we are having 18 people. Is everyone not informed? Like I saw everybody did not join the group. That's the problem. Could you tell your friends that we have a Teams group and tell them to join? So there are second year, third year, and fourth years all here. So, but there are many of second years that have not joined. I have not seen a hi from them. Any thoughts? Have you conveyed to them, like if when you go to college and all, that we people who have, you must have discussed, right? So who have joined and all. So if anyone knows why there's even the first day we have only 18 people, can ask and tell me. Am I not audible? Like this, if you don't stop me, yeah, go ahead.
Yes, Dada, you are audible.
So I just can you confirm that people have like you please as soon as you will seeing, as soon as I will be starting off with the sessions discussions, you will, if you do not interact, I would not be able to understand. First of all, your videos are not on. I don't know if you want to switch them on, you can switch them on as well, and I don't mind if you have the bandwidth, and if it is possible, it will be easier for me. And second of all, if you do not interact, I'll not be knowing. I'll be breezing through things thinking that you have understood. Okay, Adi, go ahead.
No, actually, in third year group, it was discussed that there was a session. So I think everybody knows that there
Okay.
is a session.
But people have not joined in Teams. That's why I'm saying. So there are 27 of them who have said yes, hello on Teams. There are 45 here in the groups, and 18 have joined today. So, or maybe 16, I don't know. So that's why keep them posted, that otherwise they'll not be able to, they'll be missing important things that will come up later. So I've put in a lot of effort, you'll be seeing, but if you do not want to take it, it'll be very difficult, because I don't mind people not turning up, but I don't think what ma'am will decide is, she has told me to take the attendance every day. So it's only matter of a couple of weeks. So I think you can join thinking of this as a workshop. And if you're interested, of course, if you like it, tell them. And second and fourth year, please tell your friends if you know them who have joined, right? I have made an Excel sheet as well. So I'll be uh, taking up attendance. So I don't know if you know want this grade or not, but maybe we'll have some. I'll arrange for some prize at the end if we are all interested. So people who are doing very well, I may provide some prize from my own pockets. That may be an incentive for you all. So, but for that we'll need participation, right? So, and 10% of the grade I'll be giving will be on attendance. So let's see. Uh, and this will only be uh, based on assignments, so you will not have exams. Anything that will be doing, you'll be solving questions and trying to understand. So a very only learning is the goal here, and not to judge any one of you. So if you are interested, you will be going to benefit at the end. Other than that, I have nothing to say. And before I begin, I'll introduce myself. I am a B IT pass out from 2021. I joined Indian Institute of Science in 2021 as a PhD student in Brain and Artificial Intelligence department. And some of you second years may know me. I spoke in one of your orientation sessions last year. So uh, talking about higher education and so on. So I have taken this opportunity to share some of my uh, little knowledge that I have know I've understood or experienced that is important for not only in science, career in academia, but also in if you want to excel into research and R&D in AI or data science as in the industry. So let's see how much we can learn from this, and I would ask everyone to please interact as much as possible. And if it is possible, can you please put down your names instead of your email IDs like Ajay Sen and so on. If you could, instead of your email IDs, if it is possible to join with your names, it will be very useful for me to call you out. Okay. If you could change your email IDs to as your username to your names instead, that'll be helpful. And once when you're asking questions, please interact or maybe turn on your video once so that I can see you and we may come to know each other. Okay. There's no hard and fast rule that you need to, but if anyone wants to switch on, I'll be very happy to see faces rather than blobs on the screen. So let's begin. So today we'll be discussing counting random variables and the introduction to distributions. So before we go on to learning a probability, I would try to bring your attention to how people count. So we used to count to one numbers with our fingers and so on. 1, 2, 3. We used to count that. But if there are large possibilities, for example, if you can, in this case, I have given you an example. So for example, there's a process P which can be done in k steps that I have written here. So this will be the format of how I'll be doing. I'll be writing some problems and statements on the left, and I'll be solving them on the right. So I'll be having both non-annotated forms of the PDF as well as annotated forms on the PDF on the Teams files section. You can download them and use them. So say you want to do a task which has many subparts, and each subpart you can do in multiple ways. So if you want to write down the exhaustive set of ways you can complete the task, it can be very difficult. So here the fundamentals of counting comes in. So what are the fundamentals of counting? The fundamentals of counting say that if you can break up task, a process. So why we are doing this? Because we want to see how many ways we can solve a task. We'll be understanding this why it is necessary soon when we introduce probability. So for example, a process P or a task that you want to complete has P steps or K steps that is given here. And each of the steps can be done in N1 ways. So you can perform the first step in W1, W2, WN1, right? So and second one as W1, W2, and WN2. So there are N1 ways you can complete N1 ways, N2 ways, and dot 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 NK ways, right? So for your task to be complete, you can select either, right? So you can select one from here, and one from here. So can you tell me that how many total um, ways you can do the task? So if there are say N1, N2, and so on, NK ways, how many ways can you do the task?
Multiply all of them.
Yeah, the simple thing, right? So if you are fixing this, if there are, so I'll give you why it is true. So say there are n ways to do this task, right? So this is known as induction. So n ways to do this task. So and right, so n ways. So let me write this as I n minus 1 ways to complete process 1. Let me write k minus 1 instead p2 to pk. So when you introduce this very childlike proof, but It's a formal way you write proofs. So you may have the intuition to say that it is a product of all these, but you may be required to write proofs as you are going into higher studies. So if there are ik minus 1 ways of doing the rest of the task, so if you add the first task, so you can do w1 and into w1 into ik minus 1. W2 followed by by this ik minus 1. W3 followed by ik minus 1. So on. So there will be wn1 or rather n1 ways into ik minus 1 ways of doing all the k tasks. So if you expand this, so you'll be ending up with ni I equal to 1 to k. Is that okay? So the first, to put this first option, you have k options there. So k options into the number of ways you can complete the rest of the task. So that is what it's known as a recurrence. And you can continue this for forever, and you'll get the product of all of these. Is it clear? So if there are independent ways, you come. Yeah, that's good. So whenever you are trying to write a proof, try to write something like this. Then you can, this follows by induction. So others also, I can see Arpan and Adi, I don't know what is his full name. If you could, when you speak, please introduce yourselves. It will be easy for me to remember the names then. It's very difficult to understand why the email IDs. They're so different. So the second one is is a trivial process. So if you can say, you can go from your house to the university multiple ways. You can take the metro, go to Shialda and go by a bus. You can either go by the VIP. You can go by probably through the bypass road and so on. So, or you can take the Central Avenue and then go that way. So the number of ways, and if they all don't mix with one another, so you can always do this task. So this is trivial, right? So you can do, this is n1, this is n2 dot 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 nk. If one of these tasks p1 to pk is done, p is complete. So you can complete p in how many ways? Summation of right. So is this clear? So this is just a warm up for the next what we'll be going into. So I hope this, because this is what we'll be using throughout. So I hope there's no doubt here. So let's go to the next. So now we'll be taking a bit of a detour, and we'll be trying to learn a bit of theory about probability. So 11, and I just took that opportunity to show those way of counting. I know all of you knew that, but you don't specifically know the theory related to probability. All the while in class 11 and 12, you have been using this naive definition of probability, right? The number of events that can occur, the size of the events in a set A by the total sample space. We'll come to all these, but we'll be showing how this naive definition that we have been using till now is not a useful measure to understand probabilities. See, so today, from now onwards, we'll not be studying certainty, what will happen, but we'll be associating a probability to each and every event that can happen. So we would be doing a random experiment. Right? We will do a random experiment. How will you do? And say they have some outcomes. Right? So if, for example, if you toss a coin, you'll be having head and tail as the outcome, right? So we would be going a bit abstract here because we already know these examples of head and tail die tosses and die rolls and so on. So we represent sample space or omega as all the possible outcomes of a random experiment. So say if you have, we'll do these examples. So if an experiment has some outcomes say OI, then OI must belong to the sample space, right? So if you do an experiment, for example, you do, give me an example, right? So you, for example, number of processes that is arriving to a computer at a particular CPU at a particular time. That can be 1, 2, and so on, right? So all these would be outcomes of the random experiment of the arrival of the processes. So those would be the elements of the sample space, 1, 2, and so on. So let's see. Let's take one example. So if we have an experiment that is of 2 coin tosses, what would be the sample space? I would not answer this. I would ask someone. So for a single coin toss, it is head, tail. For 2 coin tosses, what are the events that can occur? What are the possible outcomes?
Head, tail, head, tail.
Correct. So I will be writing the set as, right? This is my possible set of outcomes. So either this can happen or this can happen or this, either of these 4 things can happen. So your entire experiment is this entire experiment. And these are your possible outcomes of the experiment. Right? Similarly, if a dice is rolled, you would have 1, 2 to 6, right? As your sample space. I hope that is clear.
Yes.
So, yes. So whenever you do an experiment, whatever outcome is possible, everything will be a part of the sample space. This is what is sample space. So you have to keep these in mind. Sample space will be, I'll be always saying sample space, you'll have to immediately relate to a random experiment and the outcomes of that experiment. So let's see what are events, right? So you all this while before I go to explain what are events, do you remember that you studied in statistics the probability in class 11 and 12? The probability of an event. I would not give you the definition just yet. I'll just intuit the thing and then I'll go to the definition of an event space. So probability of an event was defined by number of outcomes in A by the size of the sample space, right? So instead of a number of elements of the sample space in A followed by divided by the, so if you have an event like this, so you have some event, so you'll have probability of A by or n A by n. This is how you have defined probability, right? Remember? So number of elements of the sample space in A by number of elements in the total sample space. This is how you define. Right? So let's do an example, you'll understand. So probability of one head in two, at least one head in 2 coin tosses. This is what you used to do with class 10 in ICSE. Exactly this formula you used to use and then used to answer. So at least one head. So what is your sample space? This is how you were taught in school days. Not even in 11 and 12, in class 10. Head, 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 tail, tail, head, and tail, tail, right? You used to write like this. And which of these are your favorable events? Which elements of the sample
First
space?
3.
Correct. So first 3 are, these belong to the event, which is the what. Now you tell me what is the event. I will build the intuition from here. What is the event?
getting two heads or getting one head, one tail.
No, the event is getting at least one head. Correct. Getting at least one head is the event. So this is your event, and the event will constitute of subsets of the sample space. This is why I was trying to intuit this. So you have probability of that event. Say, let us say this event E would be, as whoever pointed out, please introduce yourself before you answer. I'll be able to call you out. It'll be easy for me. 3 by 4, as you said. Right now, you must have a bit of understanding what are events. So an event is a, so if you, this is the definition. I'll explain this definition in just now, but based on the thing that I just showed, can you tell me formally what does it mean, or in like the high level understanding of this? What does any subset of a sample space mean? Why am I interested in this?
Like our outcome belongs to some subset of a sample space.
So okay, so an event is, so an event E, right? This can contain some omega such that omega belongs to the sample space. So for example, any event. What does that mean? So E would be a subset of the sample space, right? E would be a subset of the sample space. It can get a bit confusing here. So any event would be a collection of elements from the sample space. Is that clear? And we would be, for example, we were asking for a probability of a one head in two coin tosses. So your sample space was this. So you selected a subset from the sample space that is favorable for that event, or the event was described by that subset, right? Am I able to convey what I?
Yes.
Yeah. So I would only hear 3 people speaking. I would like to others to chip in as well. So a sample space, it is, so an event is a subset of the sample space. So what would be an event space? Roughly speaking, I'm not defining event space theoretically here. So roughly, is a set of subsets of the sample space. So we would only, for the time being, consider the power set, which consists all the subsets, right? So the power set consists of all the subsets. So for the time being, we'll only concentrate on the power set and nothing else. So I'll give you, so someone of you, please tell me what would be the event space of two coin tosses. So we define an event space by a script F. So how do you, what would be your event space of two coin tosses? So what is the sample space again? So the sample space is this, right? So what, can you give me one element in the event space? So I told
Can
you
you
a
just
set.
define the event space once again? Like,
Yeah, is the set. So we define that any event is a collection, is a subset of the sample space, right?
yes.
That you have understood. An event, it is just any subset of the sample space. So an event space would be collection of those sets or those elements, right?
Okay, so like
It's a set of
head,
subsets.
head, or head, set, like set of head, a set of head, tail. Like we
Correct.
take one of the events.
Correct. So you can have any. So these are all events from in the sample space. So you will have to create subsets. So events would be any subset. A event is any subset of the sample space. So event space would be a set of all those subsets. So once you do this example, you'll understand. Tell me. So the first one would be empty set, right?
Yes.
So empty set always belongs to a set. We all already know that by definition. So and the full set. Do you agree? What is the full set? Head, head, tail, tail, head, tail, tail, head. These two elements. This is one element. This is one element. Agreed?
Yes.
This is the entire. So this is also known as the omega. So phi and omega will always be a part of the event space. So what would be the other elements?
We take
Just
one at a time, then two at a time.
very good. That's what I wanted to know. So any subset of the so you'll be taking all the subsets of the sample space. So this is one subset. Head tail is a subset. Tail head is a subset. Tail is a subset. Right? These are all subsets. Now you'll take two at a time. So can you tell me how many will be there in total?
16.
Very good. And I'll ask you the reason a bit later. So head, 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 tail, head, head, tail, head, 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 tail, tail. So you have got how many? Three of these. So head, tail, tail, head, head, tail, 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 head, tail, tail. So you have got six of these. 1, 2, 3, 4, 5, 6. Four of these. 10, 12. And there'll be four more, right? So three element ones. And finally there'll be so 1, 2, 4. 1, 2, 3, 4, 5, 6. 6 plus 10, 12. And 4C3 is 4. 4 more. Which has three elements, right? Agreed?
Yes.
So if you want me to write them down, I can also do that. Let's do it. Head, 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 tail, 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 or rather right tail, head, 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 tail, 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 head, tail, tail, head, tail, tail, and which would be the last one? Head, 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 tail, and tail, head. Okay, head, head, tail, head, tail, tail. So I've got all the 16. So can you tell me how did I get 16? Now you should be able to use the counting rules to tell me.
It's like we can either take something or not take something. So there are two ways of for each element.
Correct. So to form so any element. So if you not understanding, then let us do it at the end. So this is a power set definition. So this is a very important thing, power set. So if you have a set, right, A, B, and C, say. A, B, C, so on. Let's write it this way. This is a set A, such that cardinality of set A is, this is the cardinality, mod A, which is number of elements. So how many subsets can you create? So what is the definition? So F is a set of all subsets. So what is the size of F? If I ask you, so if EI belongs to F, for example, right? So EI belongs to F. So in how many ways can you build EI? So as Adi was pointing out, so build EI, I will write all the A, B, so on to L. So to build AI, what EI, you can either take A or not take A, B or not take B. So how many options per sample? 2 options per sample. 2 options per element, sorry. Right? So what would be the size of the set of all sets, or the power set? Would be 2 to the power of, there are 2 into 2 into 2 into 2 into times, the cardinality times. So if you are confused, please stop me. I'll be explaining. Right? So you can either take one element or not take that element. To build one element of the subset, to build one subset, so a pictorial representation. So if you want to build a subset, say you only select these few, so others you did not select. So how did you do that? For each element, you had an option of selecting or not selecting, right? So the number of elements, the number of possible subsets would be 2 to the power of cardinality of 8. So this is why I have written that definition as the power set definition, right? Which contains all subsets of a set, right? That is known as a power set, all subsets of a set, right? I hope this is clear, right? Now, these two definition in mind, what we'll do is we will debunk the need, or we'll be showing the need of assigning probability to each of these. Assign probability to events. This is the goal of probability theory. You want to assign probabilities and not take this definition, which is naive in nature. Why is it naive in nature? So I've written it down. So you're taking each event to be equally likely. For example, I'll ask you, what is your probability of winning 25 Grand Slams? Having the number of Grand Slams more than any player in the history of tennis, you'll be saying half, because you can either win or not win. These are the two outcomes of that experiment, right? But is that correct? Did you understand? So here, all the events are equally likely. Not sensible. So for example, what is the probability that you'll be jumping out of if you jump from the earth, you'll be escaping the earth's gravity? You'll be saying half. Either you can do that or not do that. These are the two outcomes, right, of the experiment. So, but
Yes.
so you'll be saying that, so naively you'll be just saying half. So, but this is not true, because each of these events have a different probability, different likelihood of happening. We'll come to how to say that. We'll be saying why we would. So I'm trying to intuit, why do you need a specific definition for each of the events in the event space? Moreover, if this is infinite, for example, you'll be seeing, say you want to find numbers, probability of finding a number between 0 and 1 if you select a number between 0 and 4. So you are doing an infinity by infinity division. So this is one infinite set and this is one other infinite set, right? Although the answer should be 1 by 4, but you are just dividing naively by infinities, right? I think the screen is not loading. If the sets are infinite, so you'll be having so are you able to see the writing that I've written for infinite sets? Now we can see.
Just now.
Yeah, it's freezing sometimes. I'll have to look into this, how to manage this. Okay. So if you have infinite sets, you can't divide directly. So these are some of the definitions or some of the reasons we need to go into hardcore probability. Now, so we'll have a very light session today. We will be discussing some of the problems. That is, first I'll go back to counting because this is very important for understanding or calculating probability. We'll be doing combinations and seeing how many ways can you do these experiments. Here we'll be doing more problems on counting. So some of these are very trivial, so you can tell me immediately, but one of them I'll have to do it. So this is the definition of a combination NC2, that NCK is defined as n choose k n factorial by n minus k factorial by k factorial. Why is it defined this way? So from, say, if you have n objects and you want to choose k of them such that any order does not matter. So you can randomly shuffle this and finally the order between these two does not matter. So you can do this by dividing by k factorial and the rest by n minus k factorial, right? So if you have a line over here that you want to select k people and these are the seats, so this is equivalent to saying you shuffle them. There are n factorial ways of shuffling. Do you agree? Because for the first seat there are n options, second seat there are n minus 1 options, and so on. One option. So this is a probability of multiplications. So multiplication rule will hold, right? Yes. So and we say that each of this k does not matter. The arrangement of these does not matter. So we divide by k factorial. We have overcounted. Similarly, the rest of these, the permutation between them don't matter. So n minus k factorial we divided by. So this is what we are saying. We are choosing k people out of n. So that's why it's the definition of choosing or combination. So this is just the definition. We'll be seeing how to calculate such things. So let's see the first question. So I have a table over here. We'll be filling this up. So first, we have something called replacement. So replacement is here. So what do you see on the left? If you see in how many ways if you can choose k objects from n objects with replacement. This is what we are trying to find out. So what will happen? Okay, if I share, okay, I'm recording anyways from here. You can be done. So here you have something called replacement. So in how many ways can you choose k objects from n objects with replacement if the if your order matters? So you're trying to choose k objects. So you have n objects, right? So 1, 2, 3, 4, 5, dot k, right? So for each of these places, so we'll be placing some placeholders, right? We'll be placing some placeholders. This is 2a. So how many options do you have for putting in the first placeholder? Anyone? So I have n objects in a box. I have n objects. I can put them in any of these. So
First we have n choices.
So you have n choices. So I can do it in n ways. And then once I do that, I select it, I put it back to the box after noting it down what was selected because it is replaced. So again, you have n ways, right? For the second box, once you replace it back, you can again have n options for the second block, right?
Yes.
And so on till k. So how many ways can you select this or fill this up?
N to the power k.
N to the power 2.
Good. So number of ways, so 2a would be n into k times. This is n to the power k. So replacement and order matters would be n to the power k. This I'm going to leave out for some time if order does not matter. So then this is not true, right? So if your order is not mattering, so you may choose one this object k times, this object 7 times, but you can put it anyway. A1, A2, you can put them in any order. It doesn't matter. I'll come to that. Just for the time being, don't try to think about it. I'll come to that at the end. Now, without replacement, right? If you are doing without replacement, so this is very simple, right? So if you have k placeholders, k, so how many options do you have if the order matters? Your order is mattering here. So first, for the first one, if you want to place one object into the first box, so what would be the number of ways you can do that?
So for first we have n, but
Okay.
as it is without replacement,
So
it
once
is
I have
one
selected, yeah, so I have selected say object 1. So this is gone. So I have been left with n minus 1 objects now, right? Now I can only select by n minus 1 ways, right? Yeah. I'm audible. So n and the final one will be how many ways? The kth box similarly will be filled by how many ways?
N minus k.
Is it? So the second box is filled by n minus k, n minus 1. The first is filled by n. So kth would be filled by
N minus k minus 1.
k plus 1, right? So see 2, n minus 2 plus 1 is n minus 1, right? Simple. You are going to first one has all the options. Here is just subtraction. So you'll have to account for that one extra, right? So there are, so the number of ways would be 3a would be n into n minus 1, n minus 2 to n minus k plus 1, which you can all extend to 1 n minus k plus n minus k, n minus k minus 1, and so on, and divide by. So I'll just put this in bracket, n minus k, n minus k minus 1, dot 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 till 1. So this is also equal to, tell me, n factorial by n minus k factorial, right?
Yes.
So what we had a product up to n minus k plus 1. So I am going, so say 5, 4, 3. 2 and 1 are not there. So 2 and 1 I'm putting and dividing by 2 and 1. That's what I'm doing. Okay, so it's n minus k factorial by n minus k factorial, which you have popularly known in school as permutation, NPK. But we will not even think about that terminology. What we'll be doing? Divide by k factorial and multiply by k factorial. Okay. That will be n choose k, into k factorial. So I would tell you, please don't drop off. So I see a few people who have dropped off. So don't do that, because this initially may be a bit mathematically intensive, but later on you'll be seeing the big picture very soon. So and this is going to be very mathematical, because that is what you need to even understand machine learning. Otherwise you can't understand anything about it. Okay. So is this okay? So it's in another way, you choose k people, choose k objects, and permute them. Right? So order matters would be replacement no, order matters would be n choose k. If order does not matter,
So the key factorial term won't be there, like we won't be reshuffling them.
correct. So it will just be n choose k. So this is okay. No more, no reshuffling. I'm writing it down, but I'm seeing that it's not, there's a lag. I don't know why.
Yes, your video is also freezing.
Video is freezing. Okay, but my video is okay. I'm on my side is okay, but the screen is lagging, I'm seeing. So now the first question that we had left, which is this. What is it? So it says that if order doesn't matter and you are replacing things back to the system, how many ways can you choose k objects? So let's see how can we do this. Right? I'll do it at the end. Order does not matter plus replacement. That is, you need to choose k objects from n objects. Now, can anyone tell me how to do this? I will just give me some hints. I will do it anyways. So there are k objects, right? So there are k placeholders. This is how you need to think about it. You need to choose k. Or rather, here you can write. Let's do something like this. There are n objects, right? 1, 2, 3, and n. Right? So this is 1. I'm not writing k here. Be careful. Why I'm not writing k, you'll be seeing. So if I have n objects, and since order does not matter, and I replace them back. So every time I choose a ball, say there are n balls with numbers 1 to n. Every time I choose one of those balls, I can do a tally mark, something like this. Agreed? So I chose 1. So I can put a tally mark of tick, first tick. Similarly, second time when I choose, I got 3. I can put a tick on 3. Agreed? Similarly, again I got 3. I can put another tick on 3. And I'm going to continue k times, right? The number of ticks would be equal to k. Do you agree?
Yes.
Someone else? If you have a doubt, please ask me. Otherwise, it will become very uninteresting. Only 2 people will be eventually staying back. Others will all leave. So I have n objects, right? So from n objects, I'm going to select k objects. So it's equivalent to selecting one ball, noting its color down, and putting it back, right? And since order does not matter, did first three come or later three come, it does not matter, right? So I'm going to just put ticks. It will be at the end. If I get the snapshot of the ticks, that's enough. Agreed?
Yes, sir.
Okay. So what would be the total number of ticks I would be getting at the end?
K.
Okay.
K ticks. Very good.
K.
So now, can you tell me that how many ways can you arrange these ticks? What is the procedure I'll be taking to do this? So you see, so you have boxes, right? N boxes. Instead of boxes, can I replace this by separators like this? So how many separators would you have in total? So you'll have something, the new picture would be something like this, which is also equivalent. Right? Do you agree? This would be a new picture.
Yes, with n-1 partitions, right?
Exactly. They will have only n-1, these bats and balls, whatever you say, partitions, boxes, walls would be enough to separate them, right? So you will have, how many ticks will you have?
K ticks.
K ticks and n-1 partitions, right? Right? Agreed?
Yes.
So how many ways can you rearrange them? Once you are able to rearrange them, you're done. If you can do a non-permuted rearrangement, that's a combination, you're done, right? Number of ways you can rearrange them together, you will be having a solution to that, right?
Can you please explain this a bit?
Okay. So this was the first partition is giving you, say, object 1. Second part, first and second partition is giving you object 2, right? Third partition is giving you object 3. So on till object n. Do you agree?
Yes.
Okay. So now I may have ticks in a particular order. So for example, I may have ticks like this, right? And I can place partitions, k partitions anyways, to say that in how many ways did I separate the ticks out. Do you agree? So object 1 was selected 2 times, object 3 was selected 1 time, n minus k, n was selected 1 time, and n minus 1 was selected 1 time. So think of it like this. So this is a, say, think this is a ball, right? These are 2 balls. Here you have another ball. So you want to put, so you want, what you want to do is you want to put all these k balls, right? So you have k balls, right? And k balls into n partitions, which is also equivalent to saying if you move around the partition, you would always have some amount of balls in some partitions. Do you agree or not? If you change the order of partitions.
Yes.
But that is not necessary. Like where we can have n-1 as like 4 or 5 anything, and k is equals to 2. So we can always have some empty partitions as long as n-1 is greater than k.
It doesn't need to be even greater than, because you're doing replacement, right? There is no constraint.
Okay, understood.
So what you're trying to do, so if I shuffle these, right? So I'll give you an example. Say you have four objects. So 4 objects would be 4 partitions like this. or 3 partitions, and you want to select 2 balls, say for example 1, 2, right?
Yes.
Now I can shuffle these two. I can put it here. I can change these two's position as well. I can
Yes.
change these two's position as well. All these position changes are valid, right? And I would still be
Yes.
left with a way of choosing k objects out of n objects with replacement, where order does not matter, because all I'm doing is counting in which partition how many are there. At the end of the day, you will have n partitions and balls. Say after partitioning like this, you have something like this. This is a valid partition, right? So
Yes.
in the first place, 0, here 0, here 2, here 0. This is a valid partition. Similarly, 0, this is also a valid partition. 1, 1, 0, 0. Agreed?
Yes.
Yes.
So what does that mean? So it means that you can just shuffle the balls and the bats, or the partitions and the ticks, whatever you want to call them. So you can just shuffle means how many ways can you shuffle? N plus k minus 1 factorial ways.
Yes.
But aren't we overcounting? So if I put this partition over here and I put this partition over here, both are the same things, right?
Yes.
So what will be divided by?
K factorial into n
N
minus 1.
1 factorial and
Very good. That's it. Now you have understood. So there are whatever permutations you do among these partitions, it doesn't make sense. They are all single thing, right? So but we have overcounted that in the numerator. So this turns out to be n plus k minus 1 by k factorial, or n minus 1 factorial. This is one of the most interesting problems. So we saw that we are going to select, we changed the problem into giving ticks to boxes and then converting them to partitions. So this is all you need to do in probability. Try to find out simpler versions of the same problem. It will be helpful for you. So I'll give you, so for one example you will be solving now would be this. So this is n plus k minus 1, choose k, right? This one. Now you tell me. So how positive number, question number A, how many positive number solutions? So positive integers only and non-negative integers. How many ways can you do this? So first let's do the first question. How many ways can you do it? Positive number. Let's do the second question actually. Non-negative means x1, x2, x7 can be between 0, 1, dot, dot, dot till 19, right? It can't be more than that. Agreed? Right?
Yes.
Yes.
So how many ways can you do this? I think you answer, you should be able to tell me this now after we derived.
25C6.
25C6.
25. So let me just see. Did I write this k factorial, right? So okay, correct. So how do you do that? So here also x1, x2, these are partitions, right? x1, x2, x3, dot, 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 x7. Agreed? These are partitions again. And you want to put 19 balls, right? What does it mean? It means 19 plus 7 minus 1. Choose whatever. How many? Choose 7 minus 1. Agreed? Or 19, whatever you want to write. which is 25, choose 6, right? That's what you said?
Yeah.
Yeah, that is correct. So this is part B. What about part A? How do you do this? Positive integers only?
18C.
18C6.
18C6.
No, I know you can tell me answers or something like that, but tell me how to do it.
We convert the range from 1 to 19. Like we add.
So, okay, 1 plus x1 bar, you are saying something like this.
Yes, yes.
Now your things can be becoming again, they are recentered to 0, right? So you have x1 tilde plus x2 tilde dot x7 tilde equal to 12. So which is nothing but 12 plus 7 minus 1, choose 12, which is 18, choose 12. So this was, I hope that this was interesting. You may have done.
Representation of this.
Yeah.
Is that we can visualize this as we have 19 balls.
Correct.
And between these 19 balls, we'll have 18 spaces where we can place the 6 dividers.
Exactly. That's what I also said. Effectively the same thing. Exactly. That's what you are saying. Absolutely correct. Absolutely. They're equivalent. I can show you. So you have a 19 balls, right? Right. And you can put just 6 dividers. That's what I was saying. So I showed boxes and converted them into dividers. Once you do that, you are putting those dividers. You can permute them in any order, right? Very good. So who told me this? You can introduce yourself just once. It will be useful.
Brahmojit Rai, ITUG2.
Bro, okay, Brahmojit. That is correct, Brahmojit. Absolutely. I hope now this is clear. So if anyone else has some other visualizations or ways to look at it, it's good because this is all we'll be doing. It's see, probability is not about doing any calculations. It's just about simplifying thought, nothing else. So if anyone else has anything to tell, anything to share, you please tell me, or we'll be going to some very interesting problems today. So you may have done these questions algebraically, but we'll be doing some new ways to look at the same problem, which are also known as story proofs. Very famous uh, ways to prove problems. So before we go into that, I hope this is clear up to this point. We have shown different counting techniques and we have also introduced what is probability. So we have laid the foundation why probability is essential. We have motivated it, and so that we can calculate probabilities, we are going to do more of counting. I hope that path is clear, right? The big picture must never be lost. If you have any question, please ask.
No, it's clear.
Yeah, I know to 3-4 people is always very clear. Others keep quiet. That's a difficult thing. And if you don't think a particular thing in my way of conveying is not clear, you just stop me immediately. I would be happy to explain. Let's see. So this thing, so for example, you had done in your school days n factorial by n minus k factorial into k factorial. This is your n choose k, right? Which is also the same thing as writing n by k factorial into n minus k factorial, which is nothing but n by n minus k. N choose n minus k. So can you tell me how can you say that they are equivalent without doing this without doing this algebra? Without this algebra?
The number of ways of choosing k objects from n objects
Yeah.
is the same as not choosing n minus k objects from.
Very good. Very good, Brahmojit. So here you're choosing. So you have the idea of story proofs. Story proofs is for equivalent statements. Find equivalent statements for both sides of the equality. This is what is the crux that you have to understand. So as Brahmojit is saying, this is choosing k objects out of n. And this is choosing n minus k objects which you don't want to choose. Right? So for example, if you are given a 15-member World Cup team, your World Cup is around the corner, you have 15-member team. The number of ways you choose your 11 players is 11 choose 15 choose 11, which is also same as number of ways you leave out 4 players. You don't want 4 players in your team, so which is also 15 choose 4, right? I hope this is more interesting than this objects understanding, right? Now next one. Yeah, question. Okay, so left hand side. So the algebra you can do at home. It's very simple. Left hand side, how will you say is equal to? Give me an argument to show the equivalence of left and right hand side. Can anyone tell me? And you will get all these videos uploaded to the Teams channel. So the only reason of using Teams is everything will be integrated. Your assignments would be graded automatically. Everything will be done automatically once I post the solutions there. And everything will be there. So your notes and everything will be there in Teams. In the file section, I've also put a student discussion section in case you want to discuss questions with your friends. You are doing this, you can put down questions, interesting questions, you can answer each other. And in the case someone is not able to answer, I'll try to chip in. Okay. The Teams is very useful in this way. So can you tell me how to do this? So the same way Promji told me to choose k people or n people there, n minus k people, can you give me a similar story proof here? Okay.
The left hand side says that choosing k minus
okay.
1 objects from n minus 1
Okay.
total objects n times. And similarly,
okay.
we can say that for the right hand side, choosing k objects out of n objects k times.
You can say, but it's not very clear. I'll show you why it is not clear. You're on the right direction. See, say you have I will give you the same example. Say you have n players in your squad. In your cricket team, say. Right? So if you have n people in your cricket team, your task here, the task is choose a team of k people with one captain. Right? Does this give you a hint? What does left hand side signify? So both the task, for this task, both the left hand right hand side are different ways of doing the same task. Can you tell me what is the left hand side, how we are doing the task, and right hand side, how you are doing the task?
For the left hand side, we are choosing.
We are choosing k people.
Yeah. No, Adi, wait. Adi, wait. So I think what is your?
My name is Ritvik.
Ritvik, you started. So you have to, whoever will start, you introduce and you tell me. Yeah.
Yeah, for the left hand side, k minus 1 players are being chosen, and then from n people there are one captain. So there is n. That is why.
Yeah, it is your.
First we choose the captain. First we choose the captain.
Good.
And then n minus 1 people from the rest of them we choose k minus 1 players.
Very good. I'm so happy. First choose the captain. Second, choose the rest of the team.
And for the right hand side, the process is the other way around, where we choose all the players first, and then from among the players we choose one captain.
Good. This is just the way of why am I doing this story proofs? Because this will give you a way of thinking, which is very important in probability. Right hand side, you choose the team. Choose the captain from the team. Good. Now third one, Adi. What is your full name, Adi? Can you tell me? So that I can Aditya or something.
My full name is Aditya Mayuk. I'm from IT UG3.
Yeah, you're from? I can't hear you. There's a
IT
Well-
UG3.
UG3. You're Aditya Kumar.
Aditya Mayuk.
Okay. So Aditya, you tell me. Is it Aditya or Aditya?
Aditya.
Okay, Aditya, tell me. Can you tell me this one? This is also on the similar lines.
Yeah,
So
just easy one.
this you can do something like a binomial theorem as well and show that, but this is not, we are not going to do this. You can match coefficients and show it, but we'll not do this. You can try it at home, but we'll do something without that. Again, story proof. What is the task? First, tell me the task that you want to complete.
Okay.
Yeah, go ahead, Bromojit.
The total number, the task on the left hand side is to choose k objects from a total of m plus n objects.
Yeah, make it a bit interesting. We want an interesting story.
Okay, like if I have m plus n cars,
You have
and I
n
can
plus n. Okay, go ahead.
and I have to choose k cars from the total of them, from the total
Okay.
set.
Okay.
What I can also do is I can split that into a set of m objects and n objects, and
Correct.
n cars and k cars.
Okay.
Select j from the first set, k minus j from the next set.
Yeah, let's. That is very close. Let me. But since you said cars specifically, we can say maybe BMWs and Audis, or Marutis and Tata. So Maruti and Tata, you can have Maruti cars and N Tata cars, and then you have to choose K cars from them. You can. Yeah. So I'll take your example only. I was thinking on the lines of if you have a mixed doubles team, a mixed team of men and women, then also we can do that. So anyways, cars will do. We have M Maruti cars, Maruti Suzuki, and N Tata cars. You want to choose K cars, right? So left hand side is just M plus N choose K. So choosing M K cars from M plus N cars. There's no doubt. And the right hand side would be, so right hand side is a mixture of two things. Can you tell me both the addition rule and the multiplication rule? Do you agree to that? So you can do it in multiple ways. So you have to do. So one way is K Tata cars, 0 Maruti cars. Right? Similarly, K minus 1, comma 1, and so on till 0, comma K. Agreed? So if you want to select J Marutis and K minus J Tata, so how many ways can you do that? M choose J and N choose K minus J. Do you agree? Yes or no? Other than Brahmojit.
Yes, sir.
Good. Don't call me sir. So j equal to 1 to j equal to 0 to k, right? So this is j equal to 0, j equal to 1, and so on, j equal to k. Understood? So you can take either of these paths, and this would be equivalent. So each of this path is again a product of two paths. So it's a sum of products sort of a system. Okay. So now enough of counting and building the intuition of how to use these tools of combinatories in our daily life. So we'll come to probability now in the last 45 minutes of our session today. We'll be finishing off introducing probability on an event space. We'll also define a random variable and see a couple of random variables. Okay. A probability space is a three tuple, which will not be going into some measure theory definition. So we have understood these truths, right? Details I'll not go into, but I'll explain the understanding. These two you have understood. What are these two? I can ask anyone. It's from the first half of the session.
One is the sample space, one is the powered event space.
Good. Sample space. And this is the event space, right? Which contains all the subsets of the event space. Okay. And P is the P we would define as the probability measure or probability. What does probability measure means? So if you have a set like this, so I'm giving you a visual representations. So this is your sample space, right? So for the time being, we are going to consider the entire all the set of subsets, okay? All the set of subsets in the event space. So do you agree that this small f belongs to the event space, which is a subset of the sample space? Just recalling everything. So I think it's not visible yet. So once it comes up, you can see. Yeah. So
I think
yeah,
it is like it's the green. So what is the green one? A for omega.
it's a small f.
Isn't it like reverse? Like your sample space is inside F.
So what is small f? Small f is a subset of the sample. It's an event, right? So it's not an event space. You are absolutely right. Sample space is within the. This is your probability for event space. That is true. This is your event space. Absolutely correct. But you would have an event which will be inside the sample space. That also is correct.
Okay. Oh, so like the other F and this F are two different things.
Yeah, this is a small. Please pardon my handwriting. Small f is a event, which is a subset of the sample space and also an element of the event space. So for all f, we will assume we will give a probability measure or the probability of the set. So that is given in this third element in the tuple. This is called this defines the probability. So instead of thinking that all the events are equally probable, we are going totally away from it. We can define each set to have its own probability, right? We have the flexibility now. Do you understand the importance of moving to this three tuple definition? Instead of saying that all of these are equally likely, I will go directly and say, I will define that this f has a probability this f has a probability this, and so on. Are you happy with my definition or not? This is no more naive that we said going to the moon has probability half. Now I will say going to the moon, I will define has a probability by jumping as 10 to the power minus 100. I can define, right? We agree?
Yes, Dada.
Yes.
So this is why it is important to define a probability space on the sample space, event space. and the measure. So we'll not go directly into the measure. There is something called measure theory, which will not be studying here because you will only be able to appreciate that once you have understood these initial thing. But it's important to understand sample space and event space. But that's why I just introduced this. So there is a lot of abstract maths that is available. So I'll not go into that. Then people will drop off. I'll have only 2 people left. Let's see. So now we have few definitions of probability, which are known as axioms. So mathematics is incomplete without axioms. So once you give axioms, you can do mathematics. Otherwise, you can't do anything with it. So, but they must be logical. For example, what is the probability of the empty set? What should be the probability of an empty set? You tell me. It should be 0.
0.
I should define it at 0. This is so all the scientists, every man with a common sense will define it at 0. A set that is nothing in it can have no probability of occurring. Similarly, if you have the entire sample space, an event will always occur from it. Do you agree?
Yes.
So if you have the entire, so the probability of the entire event. So if you are going to see what is the probability of the entire sample space, so that is whatever will happen, whatever is the outcome of the experiment will always be in the sample space. So will be there in the set. So it's part that probability is 1. So every element of this F set is getting some probability, right? So this F has this element. So this probability of this became 1. This element also has something like this, which also became 1, right? Which became 0, sorry. Do you agree? Similarly, if you have events that are disjoint, this is called another. If I have disjoint events and I say that A occurs or A2 occurs or A3 occurs or AN occurs. A1, A2, AN. If I say this, then what will happen? So if I have disjoint events, there is no overlap between these two. If all of these occur, I should be either of these occur, it's equal to saying that the sum of all the probabilities of each event occurring. Do you agree or not? These are the 3 axioms that you will be following. So if you have, this is called the linearity of disjoint. So say an event has 30% chance of happening. Another event has 40% chance of happening. So if what would be the probability of both happening if they are either happening? If they are disjoint events, they'll be equal to 0.7, right?
Yes.
Yes.
Correct. So these are all derived from the principles that you had in Venn diagrams for used to in class 3 and 4. All Venn diagrams, that is number of elements, unions of all those. So it's all derived from that. Disjoint set, if you sum disjoint sets, there's no intersection. That's why you just can sum them. That's the idea. Now, I will not, using these axioms of probability, all of you will tell me how to do these questions. So I have a set of questions in front of me. 5 questions. So first one, who will volunteer? Probability of A equal to 1 minus probability of A complement. How do I do this?
So A and A complement are mutually exclusive. So
Very good.
we can write omega as A union A complement.
So if you, very good, very good. This is your omega, this is your A, and this is your A complement. So I don't know what is happening. Again, it appears to be hacked. There's a delay. I think I should, what should I do? I should share my screen. I don't understand what to do. but I'm sharing it from here, but you are not being able to see. It's the same thing. Okay, so you're saying omega is equal to A union A complement, right? Everyone agrees? I don't know what. Wait,
Yes.
just give me a minute. Stop sharing and start sharing again. Okay, it's the problem with my tab, I think. I'll just stop and start sharing. Share screen. Okay. I hope, is it visible or not? No, not visible. Share screen, start now. Now I think it's visible, yes. We're almost at the end of today's session, but we'll finish this up. 145 minutes more. So how do you, what do you do to this? So now, as somebody was saying, Brahmajit, right? Or Aditya.
Your screen is not.
Screen is not visible yet. I can see my screen now.
Can anyone else confirm?
No, that is visible.
It is visible or not visible?
Visible.
Yeah.
Visible.
So yeah. Now Aditya, it's visible. So I think he will have to rejoin. Okay, so he said that the entire set is a union of two disjoint exhaustive subsets. Exhaustive, well, let's just write disjoint. Disjoint subsets. So if I write disjoint subsets, so what is the left hand side? From the axioms, I can write 1, right? Agreed? And right hand side is
Yes.
A plus A complement. So hence proved. Similarly, B. How can I prove B? So I'm saying A is a subset of B. So I have to say that probability of A is less than. So this is also known as monotonicity of probability. Monotonicity. So how can you prove that probability of A is less than probability of B?
Whether we can have this entire set B in which we have a set A.
Very
so now
good.
we can have two regions in the set B. One is A and the other is B minus A.
Ah, very good, very good. I understood what you're saying. So you're saying B would be B minus A union A, right?
Yes, sir.
Good. I want others also, please interact. So others, someone will tell me what is the right hand side going to be? Someone else who has not answered yet, not Aditya. What is the right hand side? So Brahmajit has told me that B minus A union A is these two are the sets. The B set can be written as B minus A union A. So or B minus A I'll write in mathematically, so it will make cause confusion. B without A. So can you tell me what would be the right hand side from the axioms of probability that you have written for disjoint sets?
Yes.
So
P
it
of
is
A.
probability of B without A plus probability of A. So
Good.
probability of B.
Please introduce yourself, Shubhajit.
Yes, sir.
Which IT, which year?
IT third year.
Okay. B without A plus A, right?
Now,
Plus.
if I neglect the probability of B without A, then this probability of B is already greater than the probability of A. So
Very good. So probability of any event is always greater than equal to 0 and less than equal to 1. This is another axiom. Certainty and never occurring. Both are, so this is always, this is greater than equal to 0. So if you ignore this, so you will have probability of B, which will be greater than probability of A. Very good. Next is inclusion exclusion. So I'll not do the inclusion exclusion here. I'll do it in the end so that I can solve the derangement problem over here. Let's do it. So inclusion exclusion, how do I do? So for any two events A union B, inclusion exclusion property says that you can write this as probability of A plus probability of B minus probability of A intersection B, right? So there's nothing to prove as such here. So this is if you draw a set, I think you will be able to tell me. How do I do it? Tell me. Again, using the three laws or three axioms. So three axioms are disjoint sets, complement sets, and probability of whole is equal to 1. Other than that, there is no other axioms that you can use to do it. Can you tell me?
Yes, like we can write it as
Cool.
A. Wait, like
What you can write A union B as? Try writing it as some disjoint sets, and that is the hint.
We can write it as A minus intersection A minus A intersection B plus B minus A intersection B plus A intersection B.
So you can write this as A without B, right? This is your A without B. And B. This also is enough. Agreed?
yes.
So if I put probability on both sides, I can again use the axiom. So I'll have probability of B plus probability of A given B. So why A without B? So A without B, as I think Brahmajit was telling, right? So this is equal to A without A intersection B, right? Which is also equal to probability of B plus probability of A minus probability of A intersection B. Without means subtraction. You can also do union and show that. So for this for a subset, so if A is a subset of B, A without B, probability is or B without A would be probability of B minus probability of A. Again, by the same logic as we had done previously. This is your A, this is your B, so you can, this is your B without A, right? Okay. Similarly, you can prove this by induction for n elements. So that will be sum of ai I equal to 1 to n minus probability of ai intersection a2 or aj I not equal to j plus I not equal to j not equal to k. You take 3 at a time, 1 at a time, 2 at a time, and so on. This will continue. This is because, how do you know it will continue? Because once you will be subtracting the common region, then you will have to add that region. This is how it will continue. This is nothing to this law is just by induction you can prove it. You have A union B, take union C with it, and then the same thing will follow. That's how. So you will be, how do you show that? So you'll be using A union B union C as A union B union C. and then following this same logic as before. So that will give you the answer, right? Right, do you understand? So this is probability of A union B plus probability of C minus probability of A union B intersection C. So here also you can write probability of A plus probability of B minus probability of A intersection B plus probability of C. The only trick here is A union B intersection C, which is nothing but, what is it? Anyone tell me? A union B intersection C, what is it? If you're confused, give me a show me a Venn diagram. You'll tell me. I'll show you a Venn diagram. What is it?
A intersection B intersection C.
A intersection C union B intersection C. See? So this is your A union, right? This is your A union B. Agreed?
Yes, sir.
And this is the region of interest. So if I do something like A intersection C, this is A, this is B, this is C. I will have this union B intersection C. Do you agree? This is A intersection C will be this. B intersection C will be this. And minus.
Yes. Oh, the A intersection B intersection C.
Exactly. So once you will be counting it 2 times, so you will be subtracting this up. So this will give you the equation probability. If you put it back, A plus probability of B plus probability of C minus probability of A union B minus probability of B union C minus probability of C union A plus probability of A intersection B intersection C. This is how you do by induction. So you can prove for 2. So it's proof 1 and 2. So it will be proving for any I and I plus 1. So that will hold true. So the last the question, last bit of the session. So what does it say? So let there be n cards. The question is de Montmart's problem or a derangement problem. So you have C1 cards. You may have seen this before in your school days, but we'll be doing it using inclusion exclusion. See, there you have n cards and you have n envelopes, right? And you want to know the probability that not a single envelope matches the card with its number. Can you tell me what does it mean? So for example, 1 going to n going to 1, 2 going to 3, 3 going to 2, and so on, right? Not a single envelope is going to contain its original number. What is the probability that this happens when you randomly change E's and C's, right? So with this concept of events and inclusion exclusion, we will be trying to come up with it. Can you tell me how to do this? Like, can you think of a way? Like, I know it's not easy, it's not trivial. So can you define some events that will help me? To use inclusion exclusion. Okay, I'll give you a hint. So let AI be the event that ith card is in ith envelope. Okay. If ith card is in the ith envelope, let that be the event. So now can you tell me what is the desired probability? What is the probability of the desired event you want? What is the desired event that you want? If you can tell me, I will be able to do the rest of the question easily.
The complement of this AI.
One. Yeah.
Very good. Your name?
My name is Ritvik.
Oh, Ritik. Sorry, Ritvik. So you see, union of I equal to 1 to n, right? AI, the complement of this. We want this probability. Agreed? So why do I want this probability? Because the union of this says that at least one card envelope pair matches. Right? So if one of this event actually holds true, so AI is the ith card. So each of this following event, the probability of at least one of this event that is happening. If you are taking the union of these events, right? The union of all AIs would be at least one card is in the ith envelope. Do you agree? There can be multiple. There can be all the cards that can be in the same envelope. The complement of that would be not a single card in its corresponding envelope, right?
Yes, sir.
Okay. So how do I do this? So first, if I can find probability of, so this is equal to nothing but probability of 1 minus I equal to 1 to n AI. Do you agree? Because it's the complement. By definition of the axioms, we have proved that A complement is equal to 1 minus A, right? I hope this is clear.
Yes.
So now this comes under inclusion exclusion. So how do I find this? So so tell me. So what is the first thing that you need to find? Probability of AIs, right? To find this using inclusion exclusion, which is equal to sum of AIs minus sum of A intersection IJ plus 3 at a time and so on, right? Yes or no? So what is the probability of AI? What is the probability of AI happening?
N minus 1 factorial.
Probability. So I'll use the left hand side for the diagram. This is the cards 1, 2, n. You are absolutely right. Tell me the probability. That is a number of ways you can arrange. Say I. Say let's say A1 only. So A1 is you put the first card in the first envelope, right?
Yes, doctor. And the rest
Probability.
I arrange.
Rest you can arrange anyhow. So this is n minus 1 factorial by n factorial. This is the total number of arrangements. Right? So here all the things are equally probable. So you can use the naive definition. So this is 1 by n. Agreed? Aditya, you have a question?
Yes, like we are at this is an infinite sum, right? Like,
Yes.
do we have any idea like how many like total number of AIs are there? I want to ask.
Okay, but you can put the limit there, right? I will tell you why it is. It will even work for infinite sum as well as finite sum. You'll see why it is working. You have absolutely right in that sense. Because when you these tend to 0 if it is infinite, right?
Yes.
But you have to sum n of these, right? 1 to n. So in the limit it goes to 1, right?
Okay. Understood.
Yeah. So let us assume that these n's are finite for the time being, and you can put the limit equal to limit tends to infinity later. This is the way you do convert finite rational real numbers to infinities. For the time being, let's consider this. So this sum of 1 times would be into n, right? Which is be equal to 1, right? Summation of AIs. Do you agree?
Yes, sir.
All of them are same, they're symmetric, there's no difference. Similarly, A2, A1 union A2, or intersection A2. What is the probability? I'll just take a short space and do it. In A1 intersection A2, what is the event? What is the event of A1
Both
intersection A2?
A1 and A2 got their envelopes correct.
Very good. So this is n minus 2 factorial by n factorial, right?
Yes.
Good. So how many pairs are like this are there? So if I sum
NP.
over, very good, over I not equal to j, that is equal to n choose to, I will choose any two of these I comma j. Do you agree? I hope you agree, right? This is equal to n factorial by n minus 2 factorial into 2 factorial into n minus 2 factorial by n factorial. So similarly, this goes on. So 1 by 2 factorial. So for 3, it will be 1 by 3 factorial. You can check, and so on for n by 4 factorial and so on. Very simple, because you're going to multiply k, n choose k every time, and you will be having npk here. So you will be left with 1 by k factorial. Okay. So your I equal to 1 to n, ai complement will become 1 minus 1 minus 2 factorial plus 3 factorial minus 4 factorial and so on. Understood? As Brahmajit was pointing out, so it can be approximated as an infinite sum. What is this infinite sum? What is 1 factorial minus 1 by 2 factorial plus 1 by 3 factorial? What series is this? Yes, Aditya?
I think that is exponential.
E to the power minus 1, right?
Yes.
Just check it. Use Taylor series, differentiate e to the power minus x and put the value of 1. You know how to derive an infinite series, right? You just f of x, you take the f dash x as a continuously differentiable function. So you'll be getting alternates. Taylor expansion of e to the power minus x. What is it? So f of 0, which is equal to 1, right? Plus f dash 0 by 1 factorial into x. What is f dash 0? Minus e to the power x. You put 0, so you have minus 1 into x. Similarly, plus x square, which is f double prime 0 by 2 factorial and so on. So this turns out to be 1 minus x plus x square by 2 factorial minus 3x cubed by 3 factorial and so on. Equal to 1 here, you get e to the power minus 1 is equal to 1 minus 1. What am I writing? I think, okay, e to the 1 minus 1, I think that will be e to the power minus 1, not 1 minus e to the power minus 1. 1 minus 1 plus, thank you, plus 2 factorial minus 1 by 3 factorial and so on. So this will be 1 by e and not 1 minus 1 by e. Right? F0 and F1 will be cancelled, as far as I can say. Let me just check once. F0, F dash 1 is minus 1 minus 1. So it's 1 by 2 factorial minus 1 by 3 factorial and so on. It's correct. Which is equal to this sum, e to the power minus 1. Okay. I hope you have understood the ways to do inclusion exclusion. So I'll just define conditional probability. We'll not be doing any questions regarding that, but since it is related to, yeah, go ahead.
So like before moving on, can you just explain like what does this like union of all the AIs sum equal to 1 over D means?
Okay, you want to know the significance, right? So even if you have infinite, so people may think if you have infinite sequence, right? Right,
Yes.
that may not, the probability of the derangement, so at least 1 going to 1 will go to 0. People may think like that, right? So because they are infinite, everything can be placed to anything. Do you
Yes.
agree? But
Yes.
in the limit, what is happening is that this, even if you keep on increasing this number of envelopes and the permutations, there, since what is happening, you are seeing how many, what is the probability of these not exactly matching. So there is always, as your number of options increase, the number of cards also increase. Therefore, there is a balance between both of these. Therefore, you reach a asymptote. You converge to 1 by a. The probability converges. So even with the number of n, the sequence will converge to 1 by a, with as you increase the number of n's.
Okay.
So this
So
is the
like this
limiting.
total probability means like every card like there is at least one card is placed in correct position, right? Like
This
this,
is the
this is the
probability.
union.
This is none is placed in correct position. This is complement, right?
Oh, okay. So
This one was the summation of union of AI is not a single card. At least one is placed in a correct position. I have written this here. See.
okay, understood. Thank you.
So you put a complement. You say none is there in the card in the particular position. So these things, this is very simple. I don't want to, this will not going to do any, since we have done total probability, I'll just show this. See, conditional probability is defined this way because if you see, you have to use, there's only one way you can visualize this. This is just a definition that you see, but how can you visualize it? So you have A and you have B, right? So if you say that A given B, which means say what is the probability of A happening? Probability of event A given B has happened. So B has happened, you are saying. So what is the probability of A happening? A will only happen if a outcome comes in this region. Do you agree?
Yes.
So if it will, so this is, you can simply think of the naive definition, and this is the extension to the naive definition, which says that number of elements in A intersection B by number of elements in B, which is we can divide by omega, and you'll get this. Do you understand? Okay. So this is how you define conditional probability. That is the intersection probability of intersection happening. That both are happening. Since you have given B is happening, normalized by the probability of B. So you are redefining the probability measure so that the sum is 1. Otherwise, it is proportional to the intersection. So related to this, if they are independent, what does it mean? A intersection B, right? Is probability of A given B into probability of B from this definition. If they are independent, it means probability of A given B is equal to probability of A, which also means probability of A intersection B is the product of these two probabilities. This you all know, there's nothing to iterate. But you must remember one thing. Are these two events independent? Can you tell me? A comma B, is A and B independent? Are A and B independent?
They are mutually exclusive.
So are they independent? What is the intuition? They are not independent. They're totally dependent. Why? So exclusive means dependent. People always say they are exclusive means they may be independent. They may confuse. Why? Say if B has occurred, B occurred. So A will never occur, right? So you already know if from the information you're given to by B, you already know that A hasn't occurred. So the probability of A given B is not probability of A. Is same as probability of B in this sense, right? Right.
Yeah.
Here it is. Here
Yes,
it is
like,
0. Here it is probability of A given B is 0. So there is no chance of independence here. So Bayes rule. This is very simple. So A given B is B given A. Why is it? Let us write it this way: A intersection B by B. And this you can write by, you can change the conditioning as B given A into probability of A. So there's a trick to remember. So these two will be as if you are cancelling out denominator and numerator terms to put at intersection. Joint distributions will be in the denominator division terms. That's it. That's the trick. Now, we're almost on the course of completing. Two more questions. But tell me this thing. This one is very simple. So how do you prove this? Example, prove by, this is the law of total probability. There is probability of A. How do you tell that? This is this term where BIs are exclusive events and exhaustive. Any
we define like,
idea?
yes,
Okay, tell me.
like the sample space as union of like A is equals to A intersection like sample space,
Okay.
and the sample space can be written as unions of BIs, which are all independent. Sorry, which are all mutually exclusive. So it can be distributed.
See, you are also saying mutually exclusive. So never say that. Okay. Right. Since they're exclusive, so their intersections would also be, this you don't need to even think, right? They would also be exclusive, right? This is also same as you can replace the unions and the intersections. Agreed?
Yes.
Since they are independent, since they are exclusive, so there is no intersection elements between these two terms, and then you can just do probability on both sides. Since this again is exclusive, union of exclusive events, this becomes sum of I equal to 1 to n probability of A intersection BI. So if you can divide your event space into exclusive and exhaustive events, you can use the Bayes rule directly. Very good. Very good. This proof is, I really liked your beginning to the proof. Very good. Okay, so that brings us to the end of the entire introduction to probability that we have done all this while. You have learned and all. From now onwards is the new domain. So before ending today's session, I will just introduce what the new domain is, and then we'll call it a day. Now, all this while we were defining events, right, as outcomes subset of the sample space, right? All this while we were defining it this way. Now ask you, can we formalize? So all this while arithmetic operations were not possible, were not possible on events. Do you agree? Like plus, multiplication, and so on. They don't make sense, right? And we have also not been able to, not yet able to define P in the tuple, event space, probably sample space, and probability measure. Do you agree? We have not been able to define it yet. We have been using the naive definition all this while. Do you agree?
Yes.
Having some issues. There's some issue. Let me just add this person. Just give me one moment.
Dada, do it later. I have sent the mail. Actually,
Okay, well, what is the problem? Your Teams is not
next,
working well.
actually, network issues here, and I cannot concentrate properly. That's why I asked to add my another email ID so that I can join from my mobile.
Okay, sure. So you people have your you now get your university email IDs.
Yes,
That's great. We didn't get that time. So I would have used my university. All of you could have used your university email ID. That would have been easy. Do you have your Teams
but it is
from?
not enabling by Microsoft Teams to sign in like
Or,
quiz.
Oh, you don't
or
have
it is not
subscription to that.
actually like even to everyone. Like people who have only applied.
Oh, I see. But you should also have 365. So if you are applying with that, right? I don't know.
No, actually we
No.
have
Perhaps
like
not. I,
Google
that depends.
Workspace, like some.
Oh, Google Workspace is there. Then I understand. Okay. Okay. We'll discuss that later. Let's complete the last 5 minutes of this session. So the introduction to random variables. A random variable x is the function. So we have not been able to map the probability yet. So what should we do? So now if we can map, say, head and tail to some numbers using some variable, some function f into the real number line, right? 0 and 1, say. So head is 0 and tail is 1. Now I can do problems, some operations like x less than 1, this x equal to 1, checking if it's equal to 1, and so on, right? We can do that. I'm not going to define this like very formally yet. We'll do it next day. But once I can map each of these events in the sample space to a real number line, I would be able to do some arithmetic operations. I can still say you have two tosses. I can add the outcome of the two tosses. So you have two dice. I can sum that sum of two dice, which can be between 0, 1, 2, 3, and 6, and so on. Do you agree? So this is the idea. And I will also be able to give the probabilities. How? I'll show you. So a random variable is a function that maps between the sample space and the real number line, or a subset of the real number line. So is there any doubt? So for every omega, so for say omega belongs to capital Omega, which is a, what is it? An event? Not an event, sample, or an outcome, not event. Event would be a subset of omega, not belongs to, it's not be element of omega. So it's an outcome. So x of omega would be some number, would map to the real number line. Let's not write a number. Is that clear? Or x would map between. Go ahead. You have a question, Aditya.
Oh no, sorry, no mic.
Are you able to understand what I'm saying? So
That's a question.
Yeah.
So what are we exactly doing here? That any event in the sample space,
Not event.
any possible outcome.
Outcome. Yes. So your sample space is a set of outcomes, right, of a random experiment.
Okay.
So for every outcome, say head and tail are an outcome of a coin toss, right?
Yes, sir.
So head, I will use if I am mapping x from your sample space to a real number line, I would be writing x of head equal to say 1 and x of tail equal to 0. This is all we are doing, right? So this is real number line. So this is 1 and this is 0. Okay.
Okay.
So for every outcome, every element in the sample space, you will be mapping it to the real number line. That's the idea. I'll give you some examples. For example, a coin toss. That is a Bernoulli P. What is a Bernoulli distribution? That is the probability of x equal to 1 is equal to P, and probability of x equal to 0 is equal to 1 minus P. So what does x equal to 1 mean? So I will give it like more intuition into this the next day, tomorrow. But today it means, what does this mean? Probability of x equal to 1. Can anyone tell me? This is the abuse of notation.
The probability that we are getting a head.
Yes, very good. Or this, in the probability sense, this means x inverse of 1. This is an event, right? So I'll tell this next day in details. So for example, you have this as your sample space, and this say is your event, okay, which is a subset, one event in the event space, which is a subset of the sample space. Do you agree?
Yes, sir.
And then if we map this to the real number line like this, a to b, so if, and that is being done by a random variable x, so probability of x between a and b means, tell me Brahmojit or Aditya, who was stuck? Probability of p of e, which is nothing but x inverse of a comma b. Others also please tell me what is it, or which is equal to p of e. Very good. This is, we'll do it in more detail next day. What is inverse maps and so on. The inverse map is this basically, but we'll do it again. I'll tell you once again because it's almost to the end of the session. So this is also known as the PMF, or the probability mass function. Mass function. Why is it called mass function? Because it's only called for every element. What is the mass? What is for every outcome in a discrete probability distribution? What is the mass? So these are discrete probabilities, discrete distributions. Function. So next one is a binomial NP. What is the binomial NP? In coin tosses. Probability P. So X would be a sum of I1, I2. We will do this more in details next day. These are called, say, indicators. We will not, just not think about this. So there are n coin tosses, right? Is that clear? So binomial means there are n coin tosses or n experiments of the same type. So Bernoulli is one coin toss, right? Do you agree?
Yes, sir.
And binomial would be n coin tosses, and you will be told how many heads do you have. So X would give you number of heads.
Like,
So this will give you the number of heads. Do you agree or not? Yeah.
so it's not like if I have 10 coin tosses and I'm given
Correct.
that I'll give the probability of getting 4 heads, that is this 10
That
4, 10.
no. So x, this is called a distribution. So binomial 10, 0.5 if your coin tosses. So you will be, so see x for each of these outcomes have a particular probability, right? So these are possible outcomes of the random variable x. What are the values that a random variable x can take? 1 and 0 here, right?
Yes, Dada.
So see, I'll let us say think of I1. I1 is Bernoulli P. We'll do it next day again. No, don't be tensed. So Bernoulli P is a I1. So I1, what values can I1 take? 0 or 1? Right? So what can I1 be? So I1 of a head would be equal to I1 saying first coin toss is an head is 1. Do you agree? If it is tail, it will be 0.
Yes, Dada.
I think you're not clear. So this is your random variable. And for example, Bernoulli P, this is your distribution of the random variable. We'll do what does it mean? That this is going to give you a so probability is defined on this distribution. So probability of the what values is the random variable taking? Head is being mapped to 1, tail is being mapped to 0. Do you agree?
Yes, Dada.
So then what is the probability of x is equal to 1? If it is a fair coin toss, that is equal to 0.5, or here in this case, it is equal to p. That is this parameter. Now do you understand? So with probability p, you will get a head. With probability 1 minus p, you will get a tail. Clear?
Yes.
So every time you do a coin toss, the probability of head would be p, probability of tail would be 1 minus p. See, random variables don't have probability, they are deterministic. As soon as you are going to give a outcome, it will give you a number, right? As soon as it's a function, it's a one-to-one map. As soon as you give a number, it will give you an outcome, it will give you a function. As soon as it will give you a number, that is 1 or 0. And now you are trying to say what is the probability that your random variable gets those numbers 1 or 0. So if head occurs with probability p. You only said that head will occur with probability p. Tail will occur with probability 1 minus p. Right? The random variable gives you a number. And probability gives you the probability, p gives you the probability that the random variable takes that number. Do you understand now?
So Bernoulli P, for example, if x is 1, so Bernoulli P is the probability that x is 1.
Bernoulli P is the distribution. So P is the probability that x is 1. Bernoulli is the name of the distribution. It's just a name. Okay.
So like for P, x equals to 1. So P is the probability that on the coin toss that I'll be getting a 1.
Exactly. Absolutely.
Okay. Now
And you will getting a 1 because you're getting a head. In real life, you're not going to get a random variable will map the head to the 1. As you just said, inverse of that to get the event. We'll do it that inverse thing tomorrow. So, but tell me, so this gives you the number of heads. So what is the number of heads here? It's a sum of 1 to n, right? So if each coin toss, now since we have understood the previous one, so what can I1 to IN take? What values can they take, Momoji?
each I can take 0 or 1.
Very
And
good.
that
So I1
total
is the very good. Now you have understood. So I1 will be 1 if the first coin toss is 1. I2 will be 1 if the second coin toss is 1. Understood?
yes, sir.
Ij is equal to 1 if jth coin toss is 1. So tell me what will be the probability that there will be x is equal to k? You have already done this in classes. Like you may not use random variable, but you have done this. So how many? What is the probability that x is equal to k? Just tell me from the sum. From this, you should be able to tell someone else. Tell me. Yeah, go ahead. Go,
It's
Babu,
again
tell.
like that. So it's again like that problem, right? So where we have n variables and we have only sum to
Very
n.
good. Exact k, sum to k.
Is sum to k. Yes.
Yes, and they can take values between 0 and 1. So you will
0 and 1.
choose 0
So
or
shall
1,
choose
not
the
and.
k variables.
So you'll be
Which will
choosing
take
k
one.
of the n elements, k of the n variables, right?
And so the sum is k. So I'm choosing k variables, which will be 1. The rest will be 0. Those coin tosses are the ones I got the
Very
heads
good. So
in.
p to the power k into 1 minus p to the power n minus. Yes. So p k of those will be head. So p times it will be head, and n minus 1 minus p times n minus k will be tail. Understood?
Yes, Dada. Yeah.
So they are independently. They are all independent. I1, I2 are independent. I just wanted you to think about this before coming to tomorrow's session, so that's why I introduced it today. Otherwise, I would have stopped there only. So this is known as the PDF, the probability of x is equal to k, or the probability mass function. And similarly, we'll be doing this more in details next day when we'll be doing continuous distributions, which is known as the cumulative distribution function. So x less than k. So you tell me what will be the x less than k for this?
Like p1, p2, all the way to p k minus 1 plus pk.
Very good. J equal to 0 to k, right? N choose j, p to the power j, 1 minus p to the power n minus j, which is equal to the sum of I j equal to 0 to k, probability of x is equal to j, right? Very simple. There's nothing here because it's a discrete system. 0, 1, 2, dot, 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 k. All these things can come up less than 0. So similarly, so I have two things as homework for you. We'll stop here. I want you to plot the CDF of this random variable and discuss this. Since you have a holiday tomorrow, discuss these two tomorrow. I want to see the solution. This is very simple. Whatever I have drawn written here, if you discuss the random variable thing, you'll be able to do this. Right? Or let me just do the first one, second one you do as homework. So PY. So what is the probability? You're told to find CDF, right? Well, let's leave it here today. I don't want to like give you the learning base of, I don't want to mug these things up. You just think about it and do these two questions as homework. Okay, this I'll be uploading it here only. You can see the lectures as many times you want. Like this part of it. Previously, I think you knew already. And try to solve these two, and it will give you the entire idea of what happened today. Okay. So tomorrow we'll be having a longer session. So we have planned 2 long sessions in this course, 3 hours session. I'll give you a 10-minute break in between, but others are all 2 hour 15 minutes like today. So that will not be more than 2 hour 15 minutes other sessions, but tomorrow will be a longer one because we'll be doing the entire thing of distributions tomorrow. Okay. So we'll start at 3 p.m. or you don't have a class, so 3 p.m. will be good. We'll finish by 6. Right? Do you want to share anything? Yeah, tell me.
Could you please take the statement of the derangement here?
Statement of?
Derangement here, what we are finding out actually the probability that whether a particular card will be in their own envelope is not 1 by e, right?
So you are saying the probability that the card will be not in the envelope.
Not in its own envelope, it will be 1 minus 1 by e.
So I'll just come to that. I'll just share my screen. So that question that we did, we were trying to see for the derangement one, right?
Yes, sir.
Yeah. Again, don't call me sir. I'll feel ashamed. See. So you're saying, so we divide it into inclusion exclusion problem. Here. So we said that the union of this AI to AIJs, what is that? That at least one of the card matches per pair, right?
Yes, I got that. Because my
Correct.
question is in the answer itself.
Answer is 1 by E if n is infinity.
Even if n is infinity 1 by e. So my question is, let us assume that if the question remains that what is the probability that a particular ball which was in its or envelope, whatever the number be, if a particular object was in their box one
Uh,
was in their box earlier, if we know that somehow, and after
uh,
it got delayed, what will be the probability that that particular object will be in its own box?
so from beginning you knew that it is there in its own box.
Yes, sir. So yes, sir. I knew
So
that, for example, like I somehow knew that the object will be at the box 5. After it
okay.
is delayed,
So you can do, how do you say that it is deranged? So you know 5 is in its place, right?
no, I mean, let us
Once you
not
derange
one.
it, it's gone. So 5 is there, the rest n minus 1 you can derange. Do you
No,
understand?
I'm saying that let us assume that the question has been given to me in the format and find the derangement of this card of this
Okay.
object.
Uh,
So and somehow I got the intuition. Maybe someone told me that it was earlier in the box 5. Then will my
okay.
probability change to 1 or will it remain at 1 by e?
To 1. So my question is, okay, you're saying at
It's a
least
0 to a definite number 0 or 1 or to a 1 by e.
so let there be n cards C1 to n. What is the probability that none of them matches if the envelope is arranged randomly? So you're saying you're given that you have a particular card is in its particular envelope, right?
No, I'm saying that no, in the first at first in the first situation, all the cards was deranged. I
Okay.
knew nothing. Somehow after
Okay.
some time, someone told me that this card was in the box 5 before it was deranged. So will I suddenly change
So
my answer to either
why
0 or
will
1
that
or
change? Why will, so when you're deranging, you are actually permuting the thing, right?
yes.
So once you're permuting, what is the initial distribution of the cards does not make any difference. How does it make a difference? So just think of it this way. So you have cards C1 to Cn, right? When you're deranging, you can think of it as permuting C1 through Cn and keeping E1 to En same. So when you do that, why will you would, it depends on you whether you shuffled the card 5 or not, and you would, and a random shuffling would give you the same answer. It would not be, it is independent of the shuffling. So it's whether you saw it before or not.
Rather, have you heard of that goat and car problem? See those?
Yeah, that is a different question. I'll come to that tomorrow. Monty Hall problem, I'll do it tomorrow. But this is not related to the Monty Hall problem. This is what you are saying. You there is, it's a completely different setting altogether, where you are told to change your option. So where here you are not told anything. So and you're not told, you're not opened. There you will be opening all the n minus 1 cards. We'll come to Monty Hall tomorrow. So you don't mix this up. So it's not like a Monty Hall problem here. So
One more
because,
thing.
yeah.
If I realize, I'm considering 1 by almost to be half. So how can it be possible that as the number of cards go on increasing, the probability always remains at half?
So cards are also increasing your, although your cards are increasing, but your number of ways